we're going to start on talking about soil formation, but I wanted to do a couple review section for just a few moments. And I put the chair up here for the monoliths. You don't have to have it in this second, but get it in by the time you leave today. So today we're going to be talking about soil formation factors, but I wanted to make sure everybody felt fairly comfortable about this idea of this concept of the soil volume and the soil texture and particles. And is everybody pretty cool with that? Feel fairly comfortable? There's two groups that haven't been in the labs yet, but I promise you guys are going to have a lot of practice over the next 4 weeks really, of texturing, so you have a better understanding what texture means, but as well as all these other sort of tools that we're teaching you about in the field. So pH and color so far for the people that have been in labs so far, but then later on we'll be doing more bulk density, more structure stuff. So you'll get a handle of this. It's not just me talking at you. I really want you guys to get a experience of learning how to do this on your own. So sort of the reinforcing it. But everybody cool so far? No complaints? Okay, there's a couple of people here that are still working around the labs. I know I promised I wasn't going to talk about this anymore. I think we've got the labs pretty much settled down. Tuesday's lab is going to be a little tight, so that's why we have 4 people in a couple of the bunks in the vans. But I think we're going to be okay. There's still an opportunity to move around if you want. You just can't, at this point, move into either Monday or Tuesday. Okay, so if you're in the Wednesday and you want to swap around into Thursday, that's cool. But, all right, we're good? All right. Now, the next thing we're going to talk about is we're going to start with this map here. And it's the map of the world. And you see all these different colors on this map. And these colors basically represent different types of soils. Now, they're called soil orders, and there's 12 soil orders. And we'll talk about those orders later on. But basically, each one of these soil orders are distinctly different from the other orders. Okay, this is sort of like taxonomy. Okay, these are different types of creatures. Okay? Now I put this map up here, even though we haven't talked about soil orders, because I want you to see this because it illustrates the distribution of different types of soils across the landscape. In this case, the entire planet. Okay? Now, one can certainly, without even coming into this class, you would have an idea. Well, soils are going to be different as they move across the landscape. Today, we're going to be talking about some of the factors that are controlling that distribution. What are the things, the conditions, the activities on the planet that basically control the distribution of soils? Okay? And I can spin that a different way, saying, what are those things that basically create the soils in the character that we see them? Does that make sense? Okay? Now, the next slide is basically the same sort of slide, except it's the United States. Okay, so here's the United States. This is the distribution of soils in the United States. Each one of these colors basically represent a different soil order or a different class, a taxonomic class of soil. Okay? And you can see that these are not sort of randomly distributed across the United States. We have this big, huge swath of green here, which is one type of soil. We have these browns or oranges in here, browns, moving into red, some purples up here. We have some tans out here. And if you guys think about the landscape of the United States, you can probably make some predictions already about what is controlling the distribution of these soils. Right? Yes? No? Do you think you could? I'm not asking you to do it right now. Okay. But do you think you could? Okay, well, let's talk about what those controlling factors are. Okay, and what we're going to be operating on today is what we call the soil. We're going to be talking about soil forming factors. And there's basically 5 of them. And I'm going to introduce them right away. And then we're going to basically go through each one of these factors and talk about some of the variability and the controls of each one of these factors. Soil, I'll start this as a very simple equation. Soil is a function of 5 factors. The first one is parent material. This is the thing from which it is made. Parent material is generally a rock material, but it also can be organic material. Okay, so parent material. On this parent material, a lot of things react. Okay, climate, moisture and temperature, react on this parent material and weather it, modifying it. Biota, biological organisms, us, trees, microorganisms, large fauna, microfauna, mesofauna. they act upon this to redistribute the parent material. The biota is, in fact, also controlled by the distribution. Its distribution is controlled by climate. Make sense? So these are all sort of linking together. Relief or topography. One can certainly imagine higher elevations are going to be colder or cooler than lower elevations. And it's no amazing fact that water flows downhill. So if water flows downhill, we should have concentrations of water at lower elevations, or certainly within sloughs. So now I've got relief controlling climate, which in turn controls biota. But we also know biota can, in fact, help or enhance relief. Certainly, if I don't have vegetation on a landscape, that landscape's going to weather a lot faster. Erosion. Does that make sense? Okay. The last one is T for time. Now, you hear me make this analogy more when we start talking about pH. And I've already said it to you once. If you give me a weak acid and 1,000,000 years, I will weather away anything. Does that make sense? So if I have a soil that is 1 day old versus a soil that is 1,000,000 years old, and the only variable of change is pH, or exposure to acidity, I am going to have a very different soil on day 1 than I will on 1,000,000 year. Does that make sense? Okay? And you can certainly imagine every one of these is certainly affected by time. Okay? That's the premise of today's lecture. We cool with that? Pretty cool? All right, here's that distribution. Okay? And here's that equation. Okay? The soil forming factors is a conceptual model. The function of the combined effects of these factors, climate, organisms, parent material, relief, topography, is going to create, acting upon this parent material, is basically going to create a soil. And it's going to control that distribution. Now, one little fly in the ointment. Do these things stay constant? No. Which means if they don't stay constant, this is not going to stay constant. Soil is what you see today. You come back tomorrow, that material that you're looking at may or may not be the same thing. Does that make sense? Okay. So let's start. Parent material. Okay? Parent material is basically the thing upon which the soil is made. Okay? It's organic material as well as mineral deposits. These mineral deposits are derived from chemical or physical weathering of basically rocks. Okay? This is a map. This is actually out of your book. And I don't even know what all the numbers mean. But this is basically a map of all the regolith, the hard rock, bedrock distribution of the United States. Different bedrock materials across this, or in some cases not bedrock, but parent materials. So here, number 7, this one I actually do know, is the coastal plain. Okay? That coastal plain is the product of the Appalachians and these Piedmonts. Okay? But it is not the same material. Okay? It could be mineralogically the identical thing, but it could be a smaller particle because it's weathered away physically, or it physically or chemically could be something very different because of chemical weathering. Okay? It's been transported from this, and it has also been interacted by the ocean. Okay? So I have a different parent material here than here, even though this parent material, in all likelihood, was sourced from here. Make sense? Okay. So our first controlling factor is the distribution of the parent material. Where it is, and how it's been put there, and how it's been processed to be put in that place. There are lots of different types. There are direct effects of this parent material on the soil. These are inherited effects, i.e. if I have a granitic type of material, I'm going to have a sandy parent material. It's going to be sandy. On the other hand, if I have a shaly material, like we have around here, I'm all likelihood I'm going to get an acidic type of parent material. I've inherited that from the soils, I've inherited that from the parent material. We also have indirect effects or acquired effects. These effects are produced due to the weathering or the processing of that parent material. Okay, I can start, let's go back to the granite example. I start with a very large boulder. and as it weathers, it's going to start turning into sandier material. That it's still granitic, but it's now sand, so the size has changed. The size of that material has changed. Okay? Now, there are a number of different types of rocks, and we'll talk about these later in the semester, but we're basically looking at hard rock type of material, whether it's sedimentary, igneous, or metamorphic. We're also talking, when we're talking about mineral material, we're also talking about unconsolidated material. Unconsolidated material is stuff that's not sticking together, in essence. These are the gravels, the sands, the drift materials. Okay? I've introduced this idea of texture, and I don't want you to confuse texture with the soil itself. Texture is a measurement of the soil. Okay? It can be a feature of that soil. Yeah, okay, I have a sandy soil, but that sand is not necessarily a product of that soil. That sand could have actually been transported for someplace else, been deposited here, and has become a parent material. Does that make sense? Okay. And we also have secondary minerals. Materials that are not these primary minerals that basically came from either the volcanic ejecta or have been consolidated, but basically have been processed on the surface of the planet and become another mineral through chemical and sometimes physical weathering. Okay? It started as one type of mineral, and through processes at the Earth's surface have been modified into a different type of mineral. We call these secondary minerals. These are all potential parent materials. Okay? This is the material from which that soil is born. Questions? Go.
So you were saying how the granite, like, it gets broken down and then it becomes sand. So
Right.
I remember we were talking about sand, silt, and clay. Like, can sand become clay?
Sand ultimately will become clay, but it's a long, long process. The sand is basically silica oxide. It's extremely resistant to both physical and chemical weathering. That doesn't mean, I guess go back to my give me a weak acid in a million years, that doesn't mean I can't weather it away. But some minerals are more weatherable than other, both physically and chemically. Okay? And so if I start with a sand versus a shale, start with the same size rock and I put it into acid, the shale is going to weather quicker. If I take the sand and the shale and I put it into a tumbler, the shale is going to weather quickly, faster than the sand or the granite. Now, when I put it into a tumbler, I'm not actually changing the shale chemically. I'm just changing its size. And it's the same thing that's happening to the granite. On the other hand, if I throw it into acid, I'm potentially not just changing its size, but I'm also changing its chemical nature. And that's what we start talking when we talk about physical versus chemical weathering. Physical weathering does not change the material that it's weathering except for size. Does that make sense? I mean, I'm basically taking a rock and I'm cutting it in half. I got two smaller pieces of the same thing. On the other hand, if I take a rock and I put it into acid, I'm dissolving certain things preferentially over other things out of that rock. So that rock is literally changing into something else. Does that make sense? Yes? No? Kind of-ish? All right. Does that make sense? Yeah? Okay, we got this? Now, if we look at this, so we're going to basically put this out in a flowchart. And this is straight out of your book as well. But if we look at the rocks, now we also have plants up here, and I'll talk about those in a moment. But if we look at these rocks and minerals of the parent materials, you basically can have a number of scenarios. First scenario, my soil is going to form in situ, in place, from those rocks and minerals that are right there. Okay? And there, what we call that as a residual soil. Okay? The parent material basically becomes the soil in place. Now, certainly with weathering, the surface processes of the planet, there's a lot of dynamics going on. We have wind, we have water, we have ice, okay, we have gravity. These things can move that parent material from one place, either through weathering or physically moving something, to another place. Okay? So if we have this rock and mineral material transported by water, it can be transported and deposited into lakes or streams or even into the ocean. And we have certain name for these terms. Has anybody heard the term lacustrine before? It basically means lake-laid material. Okay, so if I have this water moving into a lake, I have a lacustrine parent material. That parent material initiated someplace else. It's not lake parent material, it's lake-laid parent material. Water transported into a lake. And we can have the same thing happening with streams where it becomes alluvial, or going into an ocean where it becomes marine. If the transportation happens to be gravity, it becomes a colluvial material. And you can imagine as we move through these, okay, here's ice transportation where it's deposited by ice and it becomes till or a moraine. Or it's been ice transported and then moved by water where it becomes outwash, lacustrine, alluvial, and marine. So it goes right back to these. Or it could be wind transported and it becomes aeolian. Okay, these are the processes of moving that parent material. Okay, it is not the parent material itself. It's the process of moving it. Now, the interesting thing about this process of moving is the process of moving will potentially modify that parent material. And it will also lay it in a pattern or in a way that will affect how it is in turn weathered. Okay, the people that have been out in the field already will understand this story. Okay, but if I have a material that's being laid by a stream, and it's a stream that's around here, and we have a spring thaw, okay? Some springs are really warm, and we have a fast thaw, which means we have the streams that are just pouring out water, a lot of energy, okay? And some springs are not so warm, and the energy of the water coming out of those streams is a lot less. Now, if my material is being transported by water into an alluvial fan, a stream delta, the effect of that energy is going to lay different sized particles on the stream bed. Does that make sense? So the bigger things are going to be deposited at this one location on heavy stream flow. The same spot on a season that is a cooler season and I have less water flow, this same spot is going to have smaller particles being deposited because the high energy is upstream. Okay, you have to have high energy to carry big things. And if I don't have high energy, the big stuff is going to be dropped off earlier. Okay, so all of a sudden I have a stream delta that has a variety of different strata in it. Okay, now if that variety of different strata is going to become a soil, one can certainly imagine that the finer particles are going to be weathered at a different rate than the coarser particles. Why? Go back to our story about volume. Okay, I have a given volume. Remember that cube that I had? And I start cutting that cube up, same volume, but the finer texture is in that cube, the more surface area I have. The more surface area I have, the more interactions with the environment. The more interactions with the environment, the faster the weathering. Does that make sense? All back to the transport of the initial parent material into a new arrangement affecting how the soil is made. Cool? Questions? Good? It's just this too early or I'm that good? No, obviously not. Go.
So the names there, those would refer to like a whole like section of soil because of like how it's deposited and everything, or is it like the texture?
It's the nature of the deposit. This refers to the deposit. Okay. This lacustrine could be a lot of different types of parent material, but it's how that material has been deposited and it's sort of its arrangement in space. If it's a lacustrine deposit versus a till deposit, in our minds, we have, okay, I know how till gets transported there, and I know how lake. So I would see if I have a lacustrine, I'm going to have thin strata stuff coating. If it's a till, it's just going to be this big, huge pile of stuff. Okay. Does that make sense? Yeah. Okay. We cool so far? We good? Questions? All right, so let's move on to the next one. Climate. When we're talking about climate, for all practical purposes, we're really talking about moisture and temperature. Okay. Now with climate, we're also talking about how that climate's moving and in the interaction of it. But for all practical purposes, we're basically talking about water and temperature, or precipitation and temperature. Okay. How that water is being delivered, how much of it, how long, or how is the incidental arrival of that material, of the water. Okay. Climate. How warm is it? How long is it warm? What's the cycle of warmth and cool? Okay? Water happens to be the main agent of weathering. I mean, you think about it. Any kind of chemical reaction, not any, most chemical reactions really require water to basically be there. Okay? So if I have water in a system, I'm going to be encouraging chemical reactions. Okay, I have that water in the system. What's going to happen when I have a warm temperature versus a cold temperature? What's the rate of reaction going to happen? What's going to happen to the rate of reaction? Has anybody ever heard of the C10 rule? Okay, for every 10 degrees Celsius, the temperature increases. Reaction rates increase by 2. Okay, so I start on the tundra. And I've got water. It's a spring day, so let's say it's just 1 degree Celsius. It's just above freezing. Okay, so I have water. Now I start moving from that tundra all the way down to the tropics. Okay, where suddenly I'm in 20 and 30 degrees Celsius temperatures. Okay, so I've started at 1 and I'm now at 30. Chemical reactions have increased times 2, times 2, times 2. What is that going to mean to the rate of weathering? It's going to be dramatically increased. All right, so that's why temperature and precipitation together really drive those reactions. Now, part of this also has to do with the seasonality of it. You know, just because it's hot doesn't necessarily mean there's water. Just because there's water doesn't necessarily mean it's hot. Okay, it's the combination of these that are going to produce this drive. Okay. 3 major controls by climate. First control is organic matter accumulation. Okay. Anybody have off the top of their head, where am I going to think? If you think of organic matter accumulation, what type of scenario are you imagining? If I'm going to start seeing an accumulation of, imagine a wetland. If I'm going to start seeing an accumulation of organic matter, what's the scenario, climatic-wise, that's going to produce that?
Low temperatures.
Low temperatures, that's a good one. Why is low temperatures going to produce organic matter? It's certainly going to slow down primary production. But what else is it going to slow down? It's going to slow down decomposition. Okay? So one would think, well, damn, if I'm in the tropics, I'm going to get lots and lots of organic matter. That's where I'm going to see the accumulation, because I'm going to get lots and lots of primary production. But if I'm in the tropics, I'm also going to run into the C10 rule. Decomposition rates are also going to be accelerated. Okay, so why would I find accumulation of organic matter in the tundra? Well, plant growth is really, really slow, but decomposition rates are even slower. So I'm going to have an accumulation. Does that make sense? And then on top of that, I've got ice for a huge chunk of the year. So even when the plants are not accumulating, there's definitely no decomposition going on because there's ice. This is one of the big issues with global warming. We have these huge patches in the high latitudes where there's lots of organic matter. Well, what's going to happen to that organic matter when the climate starts warming up? It's going to start decomposing. And if it decomposes, what is it going to be releasing? CO2. Global warming. We're just going to accelerate it even more. What's the question? Go. It is. It is, or it is. That material that's being decomposed is organic material. But it's the rate of accumulation of that organic matter versus the rate of decomposition that talks about the accretion of the organic matter.
So when it's decomposed, it just kind of disappears?
As it's decomposing, it's disappearing. Okay? But so what's happening is you have the stuff that's growing, okay, and it starts, sooner or later the tree's going to die, or the leaves are going to shed, or whatever, or the organism is going to die, and it's going to fall on the ground. Okay? There's 2 things that can happen to that. It basically can stay there, or it can be decomposed. Okay? And if it's decomposed, we're taking that organic matter and basically turning it into biomass and energy and CO2. If, on the other hand, we don't decompose it, we're basically accumulating organic matter. Okay, now let's talk about another scenario. That one was the temperature scenario. Let's talk about a water scenario. Can you guys think of another scenario where we have an accumulation of organic matter? It's totally controlled. We've talked about the temperature one. There's certainly a precipitation one. And they certainly interact with each other. Go.
Underwater.
Underwater. Why underwater? This is a wetland. Why underwater? What's happening underwater? Anoxic conditions. The lack of oxygen. Okay. Now that's not to say that there are not organisms out there that can respire without oxygen. But oxygen happens to be the most common denominator for respiration. And if you're going to be a decomposer, you need to be able to respire. And if you don't have oxygen, you can't do decomposition. And as a result, organic matter will accumulate. Classic wetland. Organic matter grows up here where we need to have oxygen. That organic matter happens to fall into water, gets underneath the oxic zone into an anoxic or without oxygen zone. And the water basically controls precipitation. The moisture basically controls the amount of oxygen. And if I drop that oxygen content, I start having an accumulation of organic matter. Does that make sense? No, you guys are like, no, not a chance. Yeah, it does make sense if you think about it. There are organisms that can use other alternate electron acceptors for respiration, but oxygen happens to be the most dominant. Okay, most of the organisms that are alive are basically using oxygen. Okay, and if I take the system and I turn it anoxic, I basically take the majority of organisms in the world out of the picture. Which the organism, I mean, we're eating, we decompose stuff. I mean, that burger you had last night, you know, you're decomposing it. Okay? So if I can't have oxygen, I can't have my burger because I can't respire, in essence. And it's the same thing for all these other organisms. That's not to say that decomposition is not happening in these anoxic conditions. It's just saying that the rate of decomposition is being reduced so much that the rate of accumulation is faster than the rate of decomposition, and so you get an accumulation of organic matter. Does that make sense? Okay. Next one down is clay formations. And this is when we start talking about secondary minerals, what I introduced a little bit earlier. But clay formation is most rapid at high rainfall levels. Well, why? This goes back to that chemical reaction. Water happens to be the sort of the lingua aqua of sort of the liquid of which most chemical reactions occur. So if I have more water, I'm going to have more chemical reactions. Does that make sense? Yes? Too early. Okay, next one. Vegetation itself depends on climate. Okay, so if we're talking about biota as being one of the soil forming factors, climate has a huge impact on the vegetation. And if it has a vegetation on the impact on the vegetation, it affects the soil formation because it's affecting the biota. Right around here, this part of the country, what happens every fall? Leaves fall. We have this huge input of organic matter into the soil. Okay? Granted, it's all at the surface, but that surface material, that surface deposition, is then a food source for all different kinds of organisms that come up within and up and down and basically move that material and move it into the soil. Okay? I am modifying my soils because of leaf fall every year. Okay? Now, that's around here. Let's pick some other places. What happens if I had an environment where we were wet? We have a wetland situation. Okay? Or we have an environment that's dry, but I still have plants that are growing there, some of the creosote bushes or something like that. Okay? The nature of those plants are going to affect the amount of organic matter and the type of organic matter that moves into that soil. Those plants are then going to be the anchor for other organisms who in turn are going to affect soil processes that produce soil. Does this make sense? Okay, all being controlled by climate. All right, let's skip a slide here and let's go to this slide. Continental United States, distribution of moisture. Has anybody ever seen something like this before? Okay, so the dry west, as you move east, it gets moist. My in-laws basically live someplace around here in Tulsa, and they live in Tulsa's the northeastern, northeastern sort of region of Oklahoma. They call it green country. And it is green compared to the rest of Tulsa, the rest of Oklahoma. But this is not green compared to Ithaca. But this is green compared to the Texas Panhandle. Okay? We're basically looking at that control of moisture going east and west as well as south to north. This is the green part of the country. Okay, what does that mean though? We're talking about soils. What does that mean? Any thoughts?
Less weathering.
Well, where's going to be the less weathering? Here or here? If moisture is controlling, if water controls the rate of weathering, we're going to have faster weathering rates here based on water. Now, there are other confounding issues when we start talking about temperature. If it's hot down here and cold up there, you know, the cold is going to slow the chemical reaction rate. But I have water here. Okay? So really what this is going to be controlling mostly is organisms. And certain parts of the year, it's going to be controlling factors of weathering as well. Does that make sense? Yeah? So let's think about soil formation. Where on this map do you think you're going to have, let's just go east to west. Forget about the north-south issue right now. Where on this map do you think you're going to have faster rates of soil accumulation? And where on this map do you think you're going to have faster rates of soil destruction? East? If this was your answer, you're probably right in both cases. I have more water here, so I'm going to have faster chemical reactions. But I also have more water here, which means I'm also going to have faster rates of erosion. Make sense? Controlling the soil formation. All right, so let's keep going.
Real quick, but in the dry areas where there's no like vegetative cover, that doesn't cause wind erosion,
You potentially do have wind erosion down here.
but it's still faster, you're saying?
If you look at the whole mass of material, it's going to be faster up here. But the problem, it's not a problem, but we are also having faster growth. And because we have more vegetation, we're going to have more stabilization, which is your argument. So there's different variables across this entire spectrum. But the gross picture, faster accumulation, faster destruction over here. Okay? In fact, right here is perhaps the fastest accumulation and fastest destruction. All at the same time. Does that make sense to everybody? Go.
Now that compared to like the Pacific Northwest, like how does that? I mean, big point.
Well, we're going to start talking about yeah. In that kind of scenario, you probably would have high, but you have high moisture, and you have cooler temperatures, but not necessarily cold temperatures. You would have rates of accumulation just as fast as over here. But we're talking about sort of the general. Does that make sense to everybody? I'm sure if you went out there and you measured things, there certainly would be variables that you could measure that this would be a little bit more and this would be a little less. But in general, this is what you're seeing. Does that make sense? Cool? Not a question? It wasn't a question, right? No. Okay. All right, so if we take a transect across sort of the middle of America, and we basically look from sort of lake here all the way out, to about here, okay? We're basically looking at a transect of different types of soils. Okay, if we go back to this map, we're basically looking from here to about here. Okay? This graphic that you see, this is out of your book, but this graphic that you see up here is basically looking at what's in the soil and the depth of that. So here we're looking at a soil profile. Here's the top of the soil to a depth of 120, this is centimeters, I'm thinking. Yes, centimeters, okay? And we're basically looking at a gradient of moisture, okay? As we're over here, we're basically in permanently moist, and as we're over here, we're basically permanently dry at this component of the soil, okay? Now, as we start over here in the Great Lakes, we have basically a tree coverage. And as we move west, we move out of the trees and we move into the tall grass prairies, into the mixed short grass prairies, basically back into the deserts. Okay? So the biota is being controlled by the climate. Now let's look at what happens to the soils based on that biota. We start in the trees. Okay, every fall what happens? We have leaf fall. Organic matter is added at the surface. And if we look at this section of organic matter, where's all the organic matter? Basically on the surface. But as we move out into the plains, fire regimes change. Okay, trees can't survive. Now, that's changing as we basically control fire. The tree range is moving farther and farther west. Okay, but if we look at the natural system, the trees can't move this way because of the fire regime. So what happens is we get taken over by grasses. And in the wetter part of these Great Plains, they're tall grass prairies. Now, what happens with grasses? Grasses don't shed like leaves off of trees. Grasses shed, yeah, they die at the top, but they also shed their roots. Okay? And so as a result, you can see this bulge, or this dip, perhaps a better word, this dip in organic matter. Because organic matter is not being delivered strictly at the surface anymore. It's now being distributed farther down. And as we move farther west, we move out of the tall grass into the short grass and the mixed grasses. And you can see that as the plants get smaller, they're shedding, they're not going as deep, they're shedding less organic matter, and that dip comes back up until ultimately we get way out here, not quite in the deserts, but into sort of the edges of the deserts. We still have organic matter accumulation, but it's right up at the surface, back basically where we had it in trees. Okay, that's the depth, it's not the amount, it's the depth. Okay, the other thing that we're seeing is here we have this permanently moist zone, here we have this permanently dry zone, and then we have this zone right in here where we're seeing accumulation of calcium carbonate. Just use this as a sort of a salt indicator. Okay, as the system gets drier, salts get closer to the surface. Well, why? We had this conversation about that tunnel in between next to Mann Library, right? It's not that there's not salts here. It says as we move this way, the delivery of water is not sufficient to move the salts through the system and out of the system. In this situation, what's happening is that water is hitting the ground, and it's going into the groundwater, but it's not making it all the way down, or it's going into the ground. It's not making it all the way down to the groundwater and being lost to the system. What's happening is it's going down and it's being stored, and then through evapotranspiration, the water comes back up. Okay? When the water moves into this system, it starts solubilizing the salts. And if it starts solubilizing the salts, it makes the water salty or saltier. Okay? Those salts now move with the water. Does that make sense? And if the water starts moving back up to the surface because of evapotranspiration, with evaporation, the salts are going to be left behind. They don't evaporate. And as a result, the salts accumulate farther and farther and farther to the surface until you literally get to the deserts where you will have salt pans. The salt comes literally to the surface and it coats the surface. Does this make sense? Yes? Okay. All right. Yes, sir. Wow. I'm moving up in the world here. Okay, but that's basically this transect, and this transect is controlled. This is the moisture transect. This moisture is controlling vegetation distribution as well as the salt distribution. So you can see how the climate basically controls these distributions of 3 different soil types. Here's a temperature one. Okay, this is pretty obvious, but these are basically isopleth temperature lines. 77 degrees down here, 37 degrees up there. What's that going to do to the chemical reaction rates? One would certainly expect that down here in the Keys, chemical reaction rates are going to be a lot faster than up here in Toronto. Right? Now, just because we talk about these isopleths, and these are these averages, the mean Earth temperature, okay, but that's the mean over the entire year. These temperatures change on a seasonal basis, but they also change at a diurnal basis. And they change also based on depth. Okay? Here is a graph of ground temperature versus the time of year. Okay? Each one of these lines represents a different depth. So this line right down here is at the surface. Okay? This line right down here is 12 feet down. you can see that the patterns are very similar. But the peaks and valley of them are a lot more extreme. Right? Makes sense? Well, maybe not make sense, but can you see that? Okay. Well, what's going on? Well, the Earth is acting as an insulator. The closer and closer you get to the surface, to the air, the more and more extreme the temperature events during the year occurs. So wintertime, cold. Summertime, hot. Moving back down into wintertime. Okay? But the closer you get to the air, where the temperature extremes are more extreme, okay, the more extreme the temperature change in the soil is. Okay? So imagine this C10 roll. If this is my soil profile, that's the surface of my soil, and this is the bottom of my soil, it's colder or hotter here depending upon what time of year you are. In the summertime, it's hotter, which means chemical reaction rates are going to be a lot faster. In wintertime, it's colder. This has basically been inverted, right? Down here, chemical reactions are going to be a lot faster. Does that make sense? So as a result, we're going to see a lot more extreme events at the surface rather than at depth. A lot more of the stuff that goes on in soils is happening at the surfaces. Cool? Makes sense? Now that is a seasonal. Let's take a look at a diurnal. Okay? This is the profile through the soil. So that's the top of the soil down to a depth of 10 meters. Okay? And this line basically represents the temperature constant. Okay? What is the average temperature during the winter time? And what is the average temperature during the summertime? And you can see someplace down here, basically the wintertime and the summertime is the same temperature. They're basically the same. But you can see that at the top, not reflecting, very much reflecting this, that during the summer the temperature is hotter. During the winter the temperature is colder. But you also can see at the very top that day-night, the diurnal effect. Daytime is hotter in the day. Temperature is hotter in the day whether you're in the summertime or the wintertime. So we also have a diurnal effect here as well. So it's not just seasonal, it's not just annual, it's diurnal. Okay? So imagine what that's going to be doing to processes in the soil. Okay, let's move on. Okay, here is a plot basically showing, this is out of your book as well, but this is mean annual temperature versus mean annual precipitation. And this is the distribution of different types of ecotypes. Okay? So this graph right here is the desert. That one across the top is the tropical forest. Here's the Arctic and tundra. And you can see how the arrangement is. You can see how they react to each other. If I have not a lot of precipitation, I'm down here at the desert dry end. On the other hand, if I have a higher temperature and a higher precipitation, I basically make these tropical forests. Okay? When the temperature comes down just enough and the precipitation is still fairly high, I get these deciduous and coniferous forests. The minute the precipitation comes down enough, I move into the grasslands. Make sense? Okay? These arrangements, climate arrangements, are basically controlling the distribution of the plants. And the plants, in turn, go right back to that soil forming factor equation. Do you feel comfortable with this? Am I beating a dead horse at this point? No? You guys are still sort of good with this? Okay? We can look at the continent. This is basically the same graph, except in a different type of image. You can see the same. There's precipitation increasing this way and increasing this way. Temperature increasing this way. You know, you can sort of modify it and place it like this. And here it is. There's the distribution of these environmental types. And as a result, you're going to see different types of soils. This is not that much different than this map that we started with. Way back at the beginning, right there. Did that look that much different? Not really. This is an overlay of parent material and climate and biota. This is just climate. Okay? Cool? All right, let's move on. Let's start talking about organisms, since that's what we've been talking about for a while. Okay? The most obvious organisms are basically the accumulation of organic matter is perhaps the most obvious first step of soil genesis, the first thing that you really see. Okay, when you start, I've dropped a pile of material here. What's the first thing I'm going to start seeing? That's the first change that I start seeing. It's that organic matter accumulation. Okay, and basically what we're looking at is we're looking at humus, bad term, but basically looking at organic matter. Okay, it's being decomposed. That decomposition produces organic acids as well as byproducts of the organic material. These organic acids can react to soil minerals and basically produce weathered products. Okay, the first thing we really see is basically the accumulation of that organic matter, the darker colors. Okay, that material then is decomposed. It produces these acids, which in turn start reacting with the minerals, and we start seeing soil genesis. Okay, now the other kind of, and perhaps generally this is a little bit more mature environment, but the other thing that's really obvious when we start talking about biota is bioturbation. The organisms are moving things. The one that I like the best talking about is worms, because I think worms are these amazing creatures, both destructive and creative. Okay, but imagine one earthworm in the soil. Okay, I put leaves on top of the soil. What is that earthworm going to do? It's going to start burrowing in that, and he's going to grab that leaf and he's going to pull it down. Okay, he's going to eat it down in its nest or whatever it's called, its burrow. Okay, it's going to decompose that material. It's going to throw out casts, earthworm casts. Okay, and just by the movement of that worm through the system, it has dramatically altered that system. Well, first, it's taken organic matter that's been up here and it's moved it down here. Okay, so there's transportation. It's relocated stuff. Not only has it moved it down here, it's also eaten it. So it's transformed it. Right? It's also made this huge hole in the soil. And what's that going to do to moisture and atmosphere? It's now a preferential flow path, right? Water is going to pour down this, which it wasn't before, and air can also get down this. So I've now modified the climate around that tunnel, which means other organisms can potentially take advantage of that. Earthworm tunnels, the coatings of earthworm tunnels. Earthworms have this like mucilaginous material, and they basically coat the sides of their tunnels. The population of microbes on that tunnel dramatically increases compared to the soils around it. I start moving different types of organisms into it, into this tube. Because of one other organism, I'm going to affect all the other processes that are going on in that material. Okay, and added on to that, the earthworms brings food down for everybody. Cool? Okay. Here's an example of biological interaction on two different soils, and you can see basically two different profiles. Okay, over here we see this big, clear, white zone here. Actually, you guys remember what this horizon is called? An E horizon, okay? Versus this where we have a really rich, dark surface. In fact, the richness comes down fairly deep, okay? So what do you think is going on here? The one on the left is younger? It could be, but I would make the suggestion that the one on the left has a different type of organism than the one on the right. This one is dominated by grasses. This one's dominated by trees. Where's the organic matter being added here? Throughout to down here, top and throughout. Where's the organic matter being added here? Right at the top. Okay? How about this one? Now, in this case, this is the exact same soil. This is one organism that's doing that. This one does not have the organism. This one does. The lowly earthworm. Turns out the northern sort of hardwood forests, we have the native forests for the Northeast are a mixed nut hardwood. Lots of big nuts and smaller nuts and small mix of trees. Well, earthworms are not native to the Northeast. Basically, with the glaciation, all worms were extirpated north of the glaciation line. So all the worms we find up here, they're all exotic. Okay? The forests developed prior to the worms' arrival. So what's going to happen when earthworms start moving through the system? No earthworms here, earthworms here. What's the big difference?
They start chewing up all the debris that's gathered on top.
All this stuff up here is basically being chewed away. Okay, now, it's just a small example. If you are a large nut tree, and you depend on your nuts germinating to create the next generation, right? Okay, and if these are large nuts, and they get deposited in here, it's pretty hard to find them. On the other hand, if they get deposited here, it's suddenly a lot easier to find them. What do you think those creatures that most of us, some people call deer, and I call rat with hooves, what do you think they do? They eat them. They love them. Okay? They can't find them. They love them here too, but they can't find them as much. You can find them here. And what's happening is the population of the forest are changing. And the trees that are taking over are small seed trees, because the nuts are basically getting preferentially harvested by the deer, as well as the squirrels and everybody else. I'm not just going to blame the deer. Okay. Another big change is if this stuff gets decomposed, what do you think is going to happen to the nutrients that are stored in this? It's going to become a lot more available faster available? What is that? How do you say that? The nutrients are going to become available a lot faster. Okay? Forests tend to be what they're called tight ecosystems. They're tight. The nutrients are very tight. Okay? You have worms come into the system, and the system becomes very leaky. Okay? I.e., the nutrients are moving through the system so fast because the trees are adapted to a slow release of nutrients. The nutrients are being released so fast that the trees can't capture all the nutrients. Where do those nutrients go? Downstream. So as a result, these forests are actually losing the nutrients because of the introduction of the worm. Interesting? Okay. What do you think that's happening to the soil? If the nutrients are leaving the system, the organic matter is not accumulating at the surface, you have a very different soil. If I don't have this organic matter up here, I'm losing water storage. I'm also losing insulation for temperature changes. This stuff basically acts as a blanket. Okay? So I have less water in the system, or more extreme water events, and I have cooler soils. Cooler soils mean I'm going to have slower reactions, which means I'm going to have slower genesis. Let's keep going. There's some other extremes here. Anybody know what this is? Termite mound. Okay? These organisms are basically taking subsoil and mixing it up to the top, taking stuff above, organic matter, and moving it down. They're modifying the environment. Huge effect on soil genesis. How about these guys? Everybody seen something like this? Anybody walked in the woods and see something like this? It's a wind throw. Basically, a tree has been upended by the wind. The wind knocks it over, and the roots basically take all of the soil with it and basically spin it. Okay? That's going to modify how these soils are formed. In 2 weeks, you're going to move into an environment up at top of Mount Pleasant. We have 2 soil pits. One soil pit's in an agronomic area. It's been plowed. Another soil pit has been in a forested area. It's been timbered, but has never been plowed. Take a look at the topography of the one site versus the other site. Imagine I have a landscape of pit and mounds like this. Here's a pit, and a mound's going to form when this decomposes. What's that going to do to the microclimate of that environment? Every one of those pits is going to be the wet spot. Every one of those edges is going to be the dry spot. If I have a wet spot versus a dry spot, I'm going to have different effects in soil genesis. I'm also going to have different, I've got a low spot versus a high spot. I'm also going to have slight changes in temperature. The low spots because of cool air drainage. The high spots going to be a little bit warmer. Okay? The low spots are going to have more organic matter. They're wetter, they're cooler. The high spots are going to have less organic matter. Yes, they're better drained, but they also are better drained. Does that make sense to everybody? Okay, questions. We'll move on for the rest. We'll finish at this point. Good? We good to go? All right. Remember, hand in your stuff up here if you have any questions. And there are a couple people missed labs and things like that. Come talk to me before you take off. Okay? Otherwise, be free. Have a great day, guys.